and it's a real pleasure for me to be here tonight. I've been not been here before, but I've heard very, very good things about this centre, since its founding actually, and it's a pleasure now to come here and meet you, and I've just felt very, very welcomed into your midst, so thank you for that. Thank you. So yes, I was asked, Vanaraji asked me to talk about Buddhism and quantum physics, and although I did study physics, it was an awful long time ago, so I'm hoping that none of you know anything about physics. But I'll do my best, and we're going to sort of scoot over some of the incredible kind of paradoxes and mysteries of quantum physics, and I'll try and link it as best I can to the Dharma in the time that I've got. Yeah. The first thing I want to, I'm going to start off by talking a little bit about science and then quantum physics and its relevance, and then onto the Dharma. So until, I don't know, 120 years ago, Western science, physics at least, was based on some very classical physics, as it's called, was based on the notion that there's inanimate matter in a sort of stage of objective space and time, and the matter moves according to laws, Newton's laws of motion, and everything in the universe can be explained on the basis of matter, and energy moving in space and time. And space and time is like a stage that's present for matter to move into, which then left a question as to it was a mechanistic model of the universe. So these laws of motion of matter could explain virtually everything, from why apples fall to the ground, to why the moon orbits the earth and the earth orbits the sun and the planets revolve and the stars form galaxies, etc., etc. So it was an incredibly kind of successful notion, but it was a mechanistic notion, and it was like the universe was a giant clockwork machine, and it wasn't living; it was an inanimate machine, and we were somehow plonked into it. So I guess the notion of life, if there was, physics didn't have really a notion of life, but and still really doesn't. But if anything, consciousness was seen as a byproduct of our brains. When matter becomes complex enough to form an organ like the brain, consciousness was seen as something that arises as a byproduct of inanimate matter, and is still seen like that by most scientists, or many, many scientists at least, would see consciousness in those terms. Yeah? Now all of that started to fall apart, or at least unravel to some degree, about 120 years ago, with the birth of quantum physics and relativity. Einstein's theory of relativity and quantum physics sort of came along at the same time. There were a few little, I'm not going to be able to explain these gaps, but there were a few gaps or paradoxes in physics that had been problems that had been unsolved by the turn of the 20th century. But physicists thought, okay, well, we'll solve those. There were just 2 or 3, and then we'll know everything. And there was this sense that physics at least, would come to an end, and that all that would be left was detail, filling in the 6th decimal place, as somebody put it. And as it happens, the solutions to those few problems overturned our whole conception of what the universe is. So that happened around the year 1900. And in the next couple of decades, there was a revolution in physics that we're still sort of in recovering from, if you want to put it like that. Okay, so I'm not going to talk about relativity, apart from to say that relativity overturned our notions of time and space. So time and space were no longer static, universal, objective, out there things. Time and space became much more complex, and we still don't really know what's going on in terms of time and space. And quantum physics came along and overturned our notion of matter, of what matter was. And so between them, they overturned the notions of everything that was known. Yeah, and I want to look at quantum physics. And quantum physics is primarily concerned with the very small, with atoms and subatomic particles, the things that make up of atoms. So just to give you an indication of how small an atom is, does anybody know, if you used meters, how small an atom is? No, roughly?
10 to the minus 20.
Say that again?
10 to the minus 20.
Ah, well, you're good. Actually, you're. No, actually, that's out by quite a lot. It's 10 to the minus 10. Yeah, so you're out by several. Yeah, quite a lot. But anyway, you got the sort of sense of how small it is. Atoms are 10 to the minus 10, so that's 10 zeros and then a 1 meter. 0.000, however many zeros, and then 1 meters. So I can't get my head around numbers in that way. So I was looking up this morning at sort of analogies for that, and an analogy that I came across online was if an atom was the size of a blueberry. No, first of all, let's look at a grapefruit. So the number of atoms in a grapefruit is such that if one atom was the size of a blueberry, the number of blueberries in a grapefruit, as it were, it would make the grapefruit the size of the Earth. So imagine filling the Earth with blueberries. the whole Earth with blueberries. That's the number of atoms in a grapefruit. Something about that size. So they're pretty small. And then most of an atom is empty space. So you have a nucleus at the centre of an atom. You have loads of empty space. And then you have these particles called electrons whizzing around the outside. And the electrons, are tiny compared to the nucleus, and the space between the nucleus and the electrons is vast. So, for example, if the atom was the size of a football stadium, I don't mean just the football pitch, I mean like Wembley Stadium size stadium. If the atom was the size of a football stadium, then the nucleus of the atom would be the size of a small marble. Yeah, in the centre of the football stadium. So most of the atom is empty space. Mostly there's nothing there at all. And the atom itself is incredibly small. So the nucleus is probably around 10 to the minus 20, although I don't know about that.
Oh, that must be
That's what you were thinking about, I knew that. So you might think, okay, well, physics of the very small, the sort of properties of the very small, what relevance does that have with everyday life? Yeah. Well, it has a huge amount of impact, because if we didn't have the theory of quantum physics, if we didn't have this theory that is very successful at describing the very small, if we didn't have that, we wouldn't have things like computer chips. In fact, you wouldn't have something called semiconductors, which are what transistors are made of. And transistors eventually got made into something like computer chips. So imagine that sort of pre-electronic age, or at least pre-computerized age. Everything from the washing machine to our mobile phones depends on the theory of quantum physics. We wouldn't understand without physics, quantum physics I mean, we wouldn't have a theory at least of how electricity flows through metals. So, we're so used to living in a world of electricity flowing through everything. We wouldn't understand how the sun keeps shining. We wouldn't have that without quantum physics. So the sun's so huge, but the processes that keep it shining can only be described by quantum physics. The old theories of physics aren't adequate. Yeah? So quantum physics, although we may think of it as a very abstract, weird thing about the very small, it's governing our everyday lives and technology. It's the most successful scientific theory, at least in physics, that's ever been developed. I mean, in terms of its accuracy and its predictive power, it's the most successful theory that human beings have ever developed. It's a triumph of human imagination and ingenuity. And yet, we know that it's not complete, or it's not... The thing is that you've got this theory of relativity that talks about time and space, and you've got the quantum theory which talks about matter, and they contradict each other in very fundamental ways that I can't go into. So scientists, physicists know that one or other is wrong, probably both, or at least approximate and not complete. Yeah. Anyway, never mind that. So quantum theory, particularly when it came around, people were trying to investigate what made atoms up. What were the little components of atoms? And the models that were around at the time was that all these little particles like electrons, and then the nucleus, and the nucleus was found to be made up of subatomic particles itself, all of them were like little hard billiard balls. That matter was tiny little bits of stuff that was very, very solid. Yeah. So I've got a bit of a solid matter. So this is imagine this marble as a sort of model of what a particle looks like. Yeah. So everything was made up of little bits of balls, billiard balls or marbles, tiny, 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 and they'd interact in some way, and this universe, our phenomenal world, is made up of that. That was the kind of basic model. But you also had other things going on. You had energy in the form of waves. So light was thought to be a wave, like radio waves. We talked about radio waves. We talked about what else do we talk about? Television waves. We talked about waves, and waves were different to particles. So I've brought an example of a wave here. Would you like to hold one end of my wave machine? So I don't know if you can capture this on camera, but we've got a wave. So if we do this, can you see the wave? So what would you say is different about a wave compared to a solid bit of particle? What's the difference?
Moving.
It's more fluid.
Yes, it's moving and it's fluid. Yeah. It's moving. It's also spread out. Like this, I can hold in my hand and say is here. The wave is sort of, I've forgotten your name, I'm sorry. Lauren is happening somewhere. All the space between me and Lauren, the wave is in all of it. It's sort of moving. It's like a flow of energy moving in the space between Lauren and I. Yeah. So it's not in one place. It's spread out. And you can't say it's graspable in the way that a bit of matter is graspable. Does that make sense? Okay, so the world, thanks Lauren. The world was seen to be made up of particles and waves. Light was seen to be a wave in space, and then matter was seen to be particles. So that was classical physics. So that all started to be overturned in the around 1900. And have you heard of Young's double-slit experiment? Yeah. It's to do with particles passing through a couple of holes. Yeah. So you might have heard of it. So I've got some flip charts trying to demonstrate this. This is the only kind of experiment that you need to understand in order to understand pretty much everything that is weird about quantum physics comes down to this experiment. Not completely. Actually, quantum physics gets even weirder at times, but at least if you can grasp the weirdness on this experiment, then you'll get a bit of a sense of how our common sense notions of the world have broken down. And that is, I think, where I find the most interesting analogies with the Dharma. Yeah. In a way, what I want to do in this talk is it's not really that I'm concerned about explaining physics. For me, I want to practice the Dharma and teach the Dharma. It's just that what I want to sort of try and show is that our common sense notions of reality don't hold true when you look deeply. When you look deeply, our common sense notions of what matter is, what time is, what space is, what this phenomenal universe is, common sense doesn't get you very far. Neither does our senses, our physical senses don't reveal truth. They reveal a world that is suitable for us to move around in and get breakfast and survive and live, but they're not ultimate reality. And reality is much, much weirder than those perceptions and common sense indicate. Reality is extremely weird. And I want to sort of start if that's all you sort of understand today, that would be great, because I think then that opens us up to some of the teachings of the Dharma. Yeah. By the way, do interrupt if you want to. I was going to say heckle if you want to, or certainly ask questions, or if something's not clear. So first of all, I wanted to show one of the properties of waves. So we've had a wee go, Lauren and I, at showing you waves, but I want to show you another property of waves, which is that they can overlap and interfere with each other. So if you have a pond or even a bath of water or something, and you sort of have two sets of ripples going, the ripples will overlap and pass through each other. Does that make sense? If I drop two pebbles into a pond, it'll create two sort of concentric circles of ripples that will then meet and overlap and pass through each other. And that's what's being indicated here. I've got a light source that's passing through there's a barrier and then two slits in the barrier. And what's happening is that the light is producing sort of concentric half circles or partial circles from each slit. Can you see that? What happens is that they pass through each other, they overlap. And when they pass through each other, they interfere with each other and they form a pattern on a screen at the other end. And that pattern is of light and dark stripes. Light and dark stripes. So for example, if you know how a wave has a crest and a trough, So when two waves are passing over each other, if the crests meet, they'll add up and form a bigger crest. If the troughs meet, they'll add up and form a bigger trough. And if one crest of one wave meets a trough of another wave, it'll cancel out. So with light, what you get is bands of darkness where the cancelling out has happened, and bands of light where the crests have met and the troughs have met, if you see what I mean. Yeah. So you get this sort of light and dark pattern. So this was one of the experiments that was used to show that light is a wave, because only waves pass through each other. A marble like this, a solid bit of matter, won't pass, on a billiard table, you don't get billiard balls passing through each other, you get them knocking off each other. Yeah? So, this was distinguished from what particles do. So in this experiment, they fired some particles from a bit of radioactive material that fires off particles. And they fired particles at this barrier, and the barrier had one hole in, that I've called A, and what you have is that some of the particles get through the barrier. I guess I haven't shown that loads of them just don't make it through. They hit the barrier, bounce off. But some of them do. Some of them make it through, and they land around here because particles travel in a straight line. Unless there's something forcing it to curve, a billiard ball will travel in a straight line. So most of them land around that area. Yeah. So these were actually electrons. So electrons were shown to be particles travelling through a little hole in the barrier that I've called A. So then they wondered what would happen if you had two holes in the barrier, A and B. And what you'd expect is that the electrons, some of them would make their way through this top hole and some through the bottom one. And so you'd expect that you get a bunch of electrons landing there and a bunch of electrons landing there. That makes sense, doesn't it? Does that make sense? It's like firing rocks. If you had, say you had a wall in front of you and the wall had two holes in and you were throwing rocks at the wall, a lot of them would just bounce off the wall. Some of them would make it through one hole or the other, and you'd probably end up with a pile of rocks, two piles of rocks, one behind one hole in the wall and one behind the other hole in the wall. Yeah. So that's what scientists expected to see when they fired electrons through the two holes in the barrier. But they didn't see that. That's not what happened. What happened was the electrons landed in places that indicated a pattern that was the same as the wave pattern. So imagine a rock flying through a hole in the wall, but not landing in a straight line, but doing a swerving motion and landing between where the holes are here. So rather than going there, the particles seem to go even here, where it's not sort of possible to go here unless you've followed a curvy kind of path. And the pattern that they ended up with was the same pattern as when light went through. Sort of, you end up with a pile of electrons here, a bigger pile there, a bigger pile there, the biggest pile there, where no electrons should really be seen, a smaller pile there, a smaller pile there, a smaller pile there, and none in between. So you get bands of electrons. Does that make sense? So that was weird enough, because now the electrons were behaving as waves. And what they tried to do was they thought, well, maybe the electrons are interfering with each other. So they slowed it down so that only one electron would go in at a time. And it still would land in this pattern. So it was like even one electron was behaving as a wave, as if it was going through both of those slits, one electron going through both of those slits, and then causing an interference, a rippling pattern, just like some water did. So then they couldn't work out whether the electrons were really waves or whether they were particles. When they went through one slit, they seemed to behave as particles. You introduce two slits and they seem to behave as waves, as if they were going through both slits, as if each electron was going through both slits. So then they thought, okay, let's have a look and see which slit is each electron going through. Yeah? So they set up some detectors. So this was a clever little particle detector. So if the electron's going to go through there, this detector will pick it up. And you can have another detector, if you wanted to, at the other, to catch the electrons from the other hole. As soon as they did that, as soon as they tried to measure which slit the thing went through, it stopped behaving as a wave. And you get that pattern of particles. As soon as you look, it behaves as a particle. And if you don't look, it behaves as a wave. And the two notions of particle and wave are contradictory. Yeah? You can either have a bit of stuff like this, or you can have something that's fluid and moving in space, that is spread out and then not in one place, can pass through obstacles and interfere with itself. That's very different from a bit of stuff like this. They're contradictory notions, and yet an electron would behave in both those ways. And what's worse is, it would behave in that way depending on whether you were looking or not. Yeah? So that's really weird. So somehow, what seemed to be inanimate matter now seemed to know that it was being looked at. Yeah? And would change its behaviour if you were looking. So that's weird, isn't it? Yeah, that's very, very weird. And in a way, that weirdness hasn't gone away in 120 years. People still don't know what's going on. They don't really know what's going on. All they know is that our common sense and our reason lets us down. We can't imagine something that is both a wave and a particle, and neither. It lets us down. So quantum physics, what theories of physics? Physics is written down in maths, the language of mathematics and equations, and it works. The equations describe, they predict behaviour, and it works at that predictive level. But then if you try and describe what the equations mean, nobody knows. Yeah? There are different interpretations as to what's going on. And the interpretation that when I was at university that we studied, which was at that point, the sort of most, common, popular, standard kind of interpretation, was an interpretation called the Copenhagen interpretation. Copenhagen because it was developed by a Danish man called Niels Bohr and, in Copenhagen. And Niels Bohr was like, he's like the grandfather of quantum physics. Together with Einstein. In a way, Einstein's a great grandfather of quantum physics. The two of them were sort of towering above. They were giants of the physics world. And Bohr developed this interpretation of what's happening. He was called the Great Dane. And his interpretation is that when you're not looking, an electron is neither a particle nor a wave, that it doesn't make sense to talk about what an electron is when you're not looking. And the same is true for everything. The same is true for light, the same is true for every constituent of matter and of energy. When you're not looking, it's neither wave nor particle. In fact, you can't even say that it exists objectively out there. The Copenhagen interpretation says that when you're not looking, matter is it's like a bunch of probabilities in potentialities. Matter is potentially existent in different states, but it hasn't actually decided how to exist until you look, and then it decides to exist. And the shape or the form that it exists in depends on what you were looking for. If you were looking for a wave, it will exist as a wave. If you were looking for a particle, it will exist as a particle. And when you're not looking, you can't even say that it was there. Yeah? Which is incredible, isn't it? It's like, so suddenly, this interpretation, at least, Copenhagen interpretation, started to undermine the very notion that there's an objective world out there. And Einstein, for one, hated that. Einstein, who had, in a way, his discoveries had led to some of the development of quantum theory, he hated this. He hated quantum theory. And he said, no, the world is definitely out there. It can't, it's like, does the moon exist when you're not looking? And he was saying, of course it does. But this interpretation of quantum physics says, well, we don't know, actually. We don't know if anything exists when you're not looking. Now, there are other interpretations of quantum physics. There are others, but they're even weirder. Yeah, quantum physics has it's abolished common sense. We'll never get back to a simple understanding of the world being as it appears to be. It just isn't, and we'll never get back to that. And in a way, quantum physics for me, the Copenhagen interpretation for me is one of the, the least outrageous. It is for me. I guess other scientists don't. Physicists have different opinions. There's no consensus. So why I've dwelt on all this is because the Dharma says that something very similar in some ways. Now, it's not the same, but there are interesting, parallels or crossovers with the Copenhagen interpretation, at least. So the Dharma, remember, says that we're deluded. All of us who are unenlightened we've got it wrong. That what's going on isn't what it appears. And that's why we suffer, because we've got it wrong. And the fundamental delusion that we've got wrong is that there's a real me in here and a real world out there. An independently existing me looking at an independently existing world. Yeah? That's common sense, and that is what keeps us unenlightened. And the Dharma says we've got it wrong. Instead, the Dharma says that there isn't, there is experience, but behind the experience there are no independent objects. And in here, there's no independent me. So I have an experience of, let's choose a simple thing. I can look at this beautiful red on the shrine, on the cloth on the shrine, the red and the gold. But we know that colour isn't a thing. Colour is an experience, isn't it? Colour's an experience. What physics would say is that there's waves of light, or particles of light, because it could be either, sort of bouncing off that cloth. They're sort of bouncing from the lights and the ceiling off that cloth, entering into our eyes, hitting the retina, causing some sort of electrochemical signal. The brain is interpreting that in a particular way, and we perceive red. Yeah? Or whatever your perception is. Because I can't tell if you're perceiving what I'm perceiving. We'll never know. I've got a good friend who's colourblind, and he can't distinguish between red and green. And I think what he perceives when he looks at red is neither red nor green, at least according to me. But who's right? Because after all, colour is just a perception. It's not an objectively independent thing. Yeah? That's one example of what the Dharma says we easily get wrong. We think objects are as they appear. But appearances aren't reality. Appearances are just part of our experience.
Can you just mention something that
Yeah.
happened to me the other day?
Yeah.
I have an orange glass and a yellow glass.
Oh, yes.
And I said to my partner, do you want the yellow glass? And he went to me, what yellow glass is green?
Well, there you go. And was that a surprise to you?
Yeah, absolutely.
So you didn't know.
To me, it's always been yellow, and he says it's green.
So you didn't know that he was perceiving.
Yeah.
And that must have applied to every time he saw something yellow.
Yeah, I suppose so.
So he lives in a different visual world. Yeah? And if we were, that's a really good example. And if we were a different sort of creature, say we had the, what's a different sort of creature? A bat is a different sort of creature to us, in that its visual sense is actually what we would call hearing. Yeah? But bats see by sonar, don't they? So their bat sort of experience of the world is unimaginably different to ours. Well, maybe we can imagine it, but it's very, very different to ours. And in a sense, they live in a different world because their sense apparatus is different. And which is more real, the bat world or our world? There's no more real. Does that make sense?
Yeah.
So the Dharma's saying the world isn't objectively existing out there with an independently existing me, subject, in here. All that we've got is experience, and experience is not as straightforward as we think it is. It's always an interpretation. We're always interpreting what's happening. The other thing that I want to sort of draw from quantum physics is that, an analogy at least I want to draw, is that the weird thing in this experiment and in this interpretation, the Copenhagen interpretation, is that matter seems to behave differently depending on how it's observed. So that suddenly implies that observation, looking, determines what shape reality takes, the so-called external world. So that implies consciousness is somehow involved in shaping the world. We used to think, or scientists used to just assume, that consciousness was just an experience of atoms in the brain. But actually, the Copenhagen interpretation of quantum physics starts to give a bigger role to consciousness. And what Bohr said is that it's not that the world is out there like an objective stage in which we enter. It's more that we create the world that we experience. It's somehow participatory. Through our senses and through our consciousness, experience arises and the world arises. So that is quite close to the Dharma. In fact, what the Dharma, one interpretation in Buddhism, says that actually consciousness is primary and not matter. Matter arises out of consciousness, not the other way round. That's really weird, isn't it? that we normally think that our Western scientific worldview says that consciousness arises out of matter. But what if it's the other way around? And that's what at least the Dharma implies, that consciousness is more primary, that this physical form that we've all taken has arisen out of consciousness.
Does that mean you're part of my imagination?
Well, what you see is, but what, because you're looking at me, but what you're perceiving is an image that's happening in your mind. Does that make sense?
Yeah.
So that image is sort of part of your imagination. But on the other hand, you're not seeing a giraffe. But you can't just imagine something is happening that's external to you. That's what I'm trying to say. It's not purely imagination. Something seems to be going on out there, because otherwise we could all be interpreting, some of you might be seeing, pigs flying and something. Do you see what I mean? It's not complete imagination.
Interpretation.
It's somehow to do with interpretation. Something's going on, but the Dharma says, Buddhism says, we'll never know what's out there. Something seems to be out there, but you'll never really know what's out there.
What about if there's a malfunctioning consciousness for mental health issues and things like that?
Then it'll interpret the world differently. Yeah? So it's a bit like somebody having colour blindness. They'll interpret the world differently. And who knows what that interpretation is like? It depends on the consciousness. Yeah?
Is that what is meant by ultimate and relative reality?
Well, a little bit. Relative reality is this sort of phenomenal world that we'll never really understand. You could say that ultimate reality is, as it were, its true nature.
So the ultimate reality exists whether you experience or see it or not?
Its true nature. And that true nature is said to be beyond the conceptual mind. An enlightened mind can realise it, but you can't ever put it into words or concepts.
Is that what you mean by saying the Dharma implies that?
The Dharma implies that this relative reality, as we call it, isn't really that's not ultimately true. Yeah? So we experience this relative world as objects in time and space, with me moving around, you moving around in time and space. And that works just to get around, but it's only relatively true. Yeah, it's only relatively real. And ultimate truth can't be grasped in concepts. It's a bit like the electron can't be grasped by physics. Yeah? When you're not looking. What is there? Well, physics can't tell you. In fact, it says it's not what you think it is, but we can never grasp what it is. Yeah? So yes, it's a bit like saying what's the real truth rather than what's appearances. And the Dharma says that we live in a world of appearances. And an enlightened person, a Buddha would know that. So a Buddha wouldn't mistake this for a real external object out there. They'd know that it was an experience. They'd know that red was an experience. And if we knew that deeply, not just intellectually, if we could see that with insight, we wouldn't try, apparently, and grasp onto experience and say this is me and this is mine. We'd be more able to just let experience unfold in whatever way it wants to unfold, life to unfold in whatever way it does. So we wouldn't cling to experience. And remember, what the Buddha taught is that all our dukkha, all our mind-made suffering comes from clinging. And that ultimately, if you really saw with the eyes of the enlightened person, you'd see that there was nothing to cling to. That reality is made up of, it's insubstantial. There's no solidity to anything. And physics says the same about solidity. It says there is no solidity. You know, this looks solid, but actually we know from physics, we know that it's mostly empty space. And that when you get down to the bits that you might have thought were solid, like electrons, they're not solid either. In fact, they're so ephemeral as to not even definitely be there at all. They seem to exist, at least according to this Copenhagen interpretation, in the realm of probability rather than in the realm of actuality. So that brings a whole new kind of dimension to what the Buddha meant by insubstantiality, by anatta, that nothing is solid. There is no essence to anything. He compared life to a dream. So when we dream, I had a really vivid dream last night where I was being told to read a certain book on Buddhism. And apparently I'd read it twice before, and then I read it again and I got it. Anyway, in this dream, I was in this beautiful room that was a bit like a library, but it was surrounded by Buddhas. And it was vivid, it was real. I was in that dream. I wake up and actually it's gone. And it wasn't as real as I thought. It had an effect on me. I want to read that book now. But it wasn't real in the way that waking life is real. Well, what Buddhism's saying is that waking life isn't so real either. That if we were enlightened, we'd wake up to the fact that this isn't so real. And then we wouldn't cling. And then we wouldn't suffer in the way that we do. So I'm going to wrap up now and say that, of course, Buddhism and physics say very different things a lot of the time. And this is only one interpretation of the physics. It's an interesting one. The teaching that Bhante has given is, I'm not going to have time to go into the detail, but have you heard of the Niyamas? The teaching of the Niyamas. He talks... Sorry? Vanaraji will explain it at some point. What this teaching, and as Bhante Sangharakshita has interpreted it, how it's come down to us, is that there are no essences. I mean, this is just standard Buddhism. There's no real things objectively out there. There's no real me in here. There is experience. Experiences arise in this dreamlike, rather miraculous manner that we can't grasp. They don't arise randomly, though. They arise according to certain laws. And the Niyamas describe different types of laws. And I'm not going to go through them. But one of the laws is the law of karma. And that's a really important one. Some of the laws are like the laws of physics that govern inanimate matter. But other sets of laws are the laws that govern the Dharma life, like the law of karma, that says if we act skillfully, we'll have beneficial consequences for ourselves and others, and the reverse if we don't. So what I draw from this is that there's a continuity, at least in that model, between the laws of physics and the laws of the Dharma. It's like saying this world is governed by laws, natural laws, but what we think of, it's more mysterious than what we think is going on. We can't actually say that there are things and people or selves to experience those things. What there is unfolding experience that unfolds according to these laws. So I'm going to finish by sort of trying to bring it down to our ordinary lives. The law of karma, I think, gives us a clue, because one of the consequences of there not being objectively existing things and real selves is that the notion of separateness starts to break down. And if we had time, we'd look at how in physics, the notion of separateness also breaks down. You can't really hold on to this thing that you and I are completely separate, or that anything is completely separate from anything else. And things don't exist as independent things anyway. From an ethical perspective, that means that we're profoundly connected, that consciousness is not really separate, and even our bodies are not really separate, as we know. From an ethical perspective, that means that we need to learn to relate to other people as other selves. That's what we were doing in the Metabhavana. The natural consequence of seeing the world as interconnected would be love, would be metta. And as Buddhists, that's what we're trying to move towards, is an experience of wisdom that sees our non-separateness and then responds through metta to the world around us. Yeah? And I want to finish with words by Einstein, who says very much this same thing. And I think that they're the words of somebody who saw something of the truth of the Dharma, even though he may not have called himself a Buddhist. He did know a little bit about Buddhism. So let me finish with this. A human being is a part of the whole, called by us universe, a part limited in time and space. He experiences himself, his thoughts and feelings, as something separated from the rest, a kind of optical delusion of consciousness. This delusion is a kind of prison for us, restricting us to our personal desires and to affection for a few persons nearest to us. Our task must be to free ourselves from this prison by widening our circle of compassion, to embrace all living creatures and the whole of nature in all its beauty. Nobody is able to achieve this completely, but the striving for such an achievement is in itself a part of the liberation and a foundation for inner security. So I'm going to read that again, and I'm going to turn the he's into she's, and see if you can just let those words in, because I think they're words of wisdom. A human being is a part of a whole, called by us universe, a part limited in time and space. She experiences herself, her thoughts and feelings, as something separate from the rest, a kind of optical delusion of her consciousness. This delusion is a kind of prison for us, restricting us to our personal desires and to affection for a few persons nearest to us. Our task must be to free ourselves from this prison by widening our circle of compassion, to embrace all living creatures and the whole of nature in all its beauty. Nobody is able to achieve this completely, but the striving for such achievement is in itself a part of the liberation and a foundation for inner security. So we've moved from talking about the weirdness of quantum physics to saying, look, the world is not as it appears. There's hints in quantum physics, I think, that show the truth of the Dharma. The Dharma is saying the world is really an illusion, and we can overcome this illusion by realizing that we're not fixed and separate creatures in an objective existing world. The consequences of that is love and freedom, And even if we can't reach it perfectly, the striving for that is part of the meaning of who we are. In fact, I think it is the meaning of what a human being is. So I'll leave it there with these thoughts that hopefully expand your minds and leave you with a sense of wonder. If there's a sense of wonder, I think we're more on the right track. Yeah. Thank you very much.